Okay, so let me begin once again by thanking the organizers, Soumitro, Neelima, Somdatta, Amit, of course, Rangarajan, and others who organize this fantastic meeting every year. It's the third year right now, and it's especially fantastic to actually take a look at the posters. So people who haven't done it, I mean, there's some very nice posters, and that makes it worth the while. So this year's focus has been on networks, and as some of you who were in my talk yesterday realized that I work in things very far from networks. But since this is the last talk, so I thought today I will be certainly less technical than I was yesterday, and I'll avoid a lot of equations, but tell you, story, especially for students, as to some of the fun things one can do with particles, as Sujit was saying, particles in flow. I won't be talking this time about droplets, water droplets in clouds and how they settle and coalesce, but I'm going to talk, this is really, all of this is work in progress, and most of it is being done by Jason sitting there, along with my former students, Amal Roy, Anupam, Gupta, and Narita Pal, and also in collaboration some of this with Dario Vincenzi in Nice. So I'm going to basically tell a story, and that story is simple, and that has to do with what happens when we have non-spherical particles and particles which have extended degrees of freedom. Part of this reason, and I'm sort of really new to this game, is because at some point I outgrew or got bored with droplets which were spherical in shape, but which are fun nevertheless. So I'm going to tell you two stories. One which has to do with this sort of motion, which I'll argue sort of certainly starts mimicking collective motion of microorganisms, and I'll sort of try to motivate some actually physically relevant numbers. And the other story will be about this. If you've been watching closely, this is sort of Jason's work, where he begins with chains which are nicely folded, and when you put them in a turbulent flow, these chains sort of extend out. And I'll try to convey why this is something that we found exciting. And again, it's the last talk of a long week and a school, so I'll try to avoid technicalities, but sort of just say it as a story. Okay, so in case we don't remember anything else from this talk, the only thing that I would like to you all to keep in mind is that when I'm talking about particles in turbulent flow, I'm essentially thinking of systems such as these. Of course, there are various caveats, but all I'm going to talk about is probably applicable to the microphysics of cloud formation, which is something that I work on closely. It could be applied to pyroclastic flows when you have eruptions of small dust in a volcanic setting. Then we have sort of earlier with Jeremy and others, we found some evidence which could be applied to sort of protoplanetary disks, pollutant dispersion, which in India ought to be probably one of the key problems, along with the Indian monsoon that Amit and Rama and others have been working on in industry, of course. And then there is this slide, this picture that I have shown for a few years, especially when I was job hunting, which had to do with how do you apply ideas in turbulent transport of small particles and try to see what goes on in living organisms which tend to show collective behavior. All right, so today I'm going to sort of argue that there might be a way, even if it's a very naive toy model, where certain features are reproduced. Okay, so the first part of the talk, you remember the chain for a movie, but the first part of the talk will deal with particles which are either of this or this shape, which has a certain orientation vector which sort of defines its level of orientation. And what I'm going to focus on, and this is partly because I didn't want it to be too technical, but something which certainly has an appeal for all of us when we see motion of small organisms. What I'm going to say is that we are sort of trying to think of these particles mimicking small microorganisms, really small ones. So don't think of birds, don't think of big fish, but think of zooplankton, for example. If one were to think of zooplankton, I'm not sure one does on a regular basis, but that's the sort of microorganisms or artificial swimmers that I'm interested in, and we'll see as we go along what happens. So, okay, this is a bit crowded, so ignore what's there on the slide, of course, but this has to do with this rather famous model, which is now known as the Vicsek model, which came up in the mid-90s. People in the non-equilibrium statistical physics community, which is essentially an agent-driven model. And all it says is that if you have a collection of particles, there's no flow, there is no interaction, external interaction, nothing. But if you have a collection of particles, all of which has a certain velocity v, and they can move randomly, all right? Now you impose a rule and say that each of these particles can quote-unquote see, it could be a chemical process or visual, can see a certain neighborhood of size r. For example, without my glasses, my neighborhood is very small, but with people who have better eyesight, that neighborhood is large. So that's a tunable parameter. And they can see their neighbors, and they try to sort of calculate at discrete time intervals what their neighbors are doing, and they try to go with the neighbors, all right? And when you play this game in such really simple systems, of course, I should point out that there's been tons and tons of work on this model going forward, in places in India as well, in Bangalore, groups in Chennai and other places. Essentially, what you see is that in time, there's a collective behavior which emerges. So these are sort of like model flocks. So how does a collective self-organized behavior emerge from a bunch of particles which have their own velocity, so they're self-propelled, just by applying simple agent rules so that they sort of try to see what their neighbors are doing. All right? The curious thing is that very little is known, perhaps with good reason, about what happens when you put these particles in a flow. All right? I mean, the natural question is that in all settings where living organisms, microorganisms or not, tend to show collective behavior, they're typically in a flow. That could be a marine environment or it could be air, all right? So one of the sort of the two studies that I particularly liked was the one by Nick and his student Nidhi, where they looked at small particles in a synthetic flow. So they weren't doing turbulence. That's, I'll come to that in a bit. That's a little harder. They were choosing synthetic flows which were composed of, let's say, some variation of the Ornstein-Uhlenbeck process. So it's something like a smooth stochastic flow. And they were seeing whether, by applying rather simple rules, so the rule can be written as simply as this: the position is updated at every discrete time interval delta t, just through a ballistic motion, but there's an added term which takes into account that you would like to orient yourself along the direction of your neighbors, all right? And what they showed, for example, here it's rather clear, what they showed that in time, for certain values of their, self-propelled velocity, you do indeed see a global order. So for example, here they're measuring essentially what we would call a global order parameter, which is a measure of whether there is enough collective motion in one direction, in a particular direction or not. All right. So then there was this other paper a couple of years ago by Bageley, and subsequently Bageley's group has worked a little more on this, which shows how if you have strongly vortical flows, again, these are not really turbulent flows, but these are flows which have strong vortices, and we'll see why that makes the problem rather curious. Then you see, and if you just allow self-propelled passive particles, so they're being affected by the flow, and you put in the simplest interaction rules that you can think of, and a little noise to mimic the fact that decision-making is not, absolute. Then again, Bageley and his group, actually this was a paper just by him, they again showed that these self-propelled particles seem to follow a certain behavior which is sort of reminiscent, although not exactly that, of large-scale clustering that you see. I mean, for example, in the evening, once the workshop gets over, around 6 o'clock, you see these homing birds here, and they sort of also show this behavior. Okay, so what we were curious, and the story starts a few years ago, actually, with Ashok and Divya, Ashok was a student here, he's now doing his PhD in the US, we had a sort of rather simple question, which is, what happens when the carrier flow is turbulent? It's more complex, and the only complex flow that I know a little how to handle is the turbulent flow. Okay, I mean, one could of course have other levels of complexity. And what happens when these particles are tracers? So the earlier work that I showed you, both Nix and Baglay's, dealt with particles which were tracers. So they followed the fluid exactly. Okay, so however, the question that we asked was that in general, most of these organisms are not tracers. They have a finite size, they have a finite density, which is different from the flow. And in that case, are there special sizes, are there special densities which seem to flock? And if we find them, do they agree with what one observes in nature? All right, so our strategy was essentially to take, and this is the sort of key slide for the story, was to take small but finite size self-propelled particles. So they have a little self-propelled velocity. And in our model, we allow both Vicsek-like alignment, then there is self-propulsion, and then there is the effect of turbulence, which tries to sort of scramble things up. And we would like to see under all these competing interactions, and there's of course noise, but I won't dwell too much on what the noise is doing to this problem. Under all of this, under all of these sort of reasonably defensible, hopefully, assumptions, do we see the emergence of a collective behavior? Now, so this is a little digression. Now the question is, what's so special about about finite size particles? Why am I laboring on the point that let's move beyond the tracer limit? The reason has to do with what's known as preferential. Yeah, you had a question? Yeah. I will sort of look at each effect of each of these additions later, individually, but it's perfectly sort of reasonable to have a model which it's not as complicated as it sounds. That's why I'm doing it. So when I come to the equations, you'll see that sort of it's not that bad to have all of them, and then you can turn off each of these parameters and then see what's the role of one versus the other. All right. And the reason why yeah, Amit.
For you, the tracers includes inertial particles?
No, for me, tracers are particles whose, exactly.
Just 2 slides back.
Yeah.
So, yeah, here.
Yeah.
These ones don't look Lagrangian.
No, they
just going round and round.
Exactly, they don't. That's because of the rules that he imposed on their interaction. So, yeah, so all of this, of course, if it's Lagrangian, then you will have something which fills up the full phase space accurately. Yeah, exactly. So that brings me to the following point. The reason why, why we felt that this should be an important feature is because of the following thing that people in turbulence have known for quite a long time. And it's the following. If you do not have Lagrangian particles, the sort of particles that Amit was talking about, which faithfully follows the flow, but if you have a finite size particles, then their dynamics is dissipative. And they tend to preferentially cluster. A mechanical way, for example, you see these particles, or these which are even nicer actually, they look like a fish egg actually.
That will happen even if they are spherical particles.
That's right.
Non-spherical.
Yeah, so I'll come to that. So this is a digression where I'm just talking about the issue of preferential concentration in general, which happens also for non-spherical particles, all right? Okay. So the point is that these guys tend to segregate, all right? If you want a mechanical way of understanding this is that often these vortical regions centrifuge these heavy particles out and they don't follow the full sort of the phase space of the flow completely. All right, so what happens is the following. So one of the ways that preferential concentration is quantified, and I don't want to dwell too much on this, is to actually look at what's known as the pair sort of version of the pair correlation function. You ask yourself, what's the probability of having two particles within a distance r? And that scales as r to the power d2, which in the community of turbulent transport, in their jargon, in our jargon, it's known as the correlation dimension. So if your tracers, you're sitting somewhere here, the so-called Stokes number, which is a measure of the finiteness of your particle, your so-called Stokes number is 0 for a tracer. You span the whole phase space. So if you're in a volume of radius r, then you're likely to have r cubed number of particles, right? Because you're uniformly distributed. However, if you have finite Stokes, you start decoupling from the flow because you have a finite response time scale. And so you sort of scale with volume as r to the power d2, where d2 is less than 3. All right, so this is what's known as preferential concentration. And when your Stokes number is large, you again get back to the uniform distribution. That's because the particle responds so slowly to the flow that it really doesn't care what the flow is doing, and hence it again fills up the whole phase space. It's the ones in the middle which are the dicey characters, and they sort of don't want to follow the flow too closely, and yet they follow it a little, and so you end up with this maximally concentrated particles. And so if you take snapshots of particles with different sizes, you do see that they cluster. You have these voids, and the black points are regions where the particles have clustered. So the reason this was interesting, this, I'm now connecting it to the Vicsek or the collective motion picture. The reason why we felt this was interesting was because of the following reason. Within there's a whole class of these models, but within all these agent-driven models, Vicsek type models, you impose a certain radius of interaction. And within that radius, you see what your neighbors do, and you try to do that. What Ashok, Divya, and I felt was that if you had a mechanical mechanism which allowed more and more of these individuals to be pushed in the small region interaction sphere of R, then the chance of that flock stabilizing is going to be higher. That's because you see more and more of your neighbors for reasons that you do not have control on. It's just the mechanics of the flow and the fact that you have finite inertia. So you're all pushed in a smaller region, and imagine the Q is visual, so you can see many more individuals around you, and there's a higher chance that you will flock more effectively. And rather counterintuitively, although turbulence is playing around and mixing and taking things far away from each other, etc., rather counterintuitively, it might be a situation where turbulent flow actually helps stabilize flocks for certain sizes which have to do in this range. All right? So this was the sort of naive game that we were playing, and now I'll sort of try to make this model. The danger is in trying to sort of artificially make this model more realistic. I run into more difficulties, but let me nevertheless stress what we are doing. Okay, so what we're going to do is the following. Our flow will be a solution of the three-dimensional Navier-Stokes equation. So it will be a fully turbulent thing, and we are going to choose Reynolds number, which are sort of close to what you find in the deep sea. Then we choose a whole bunch of particles which are both spherical and non-spherical, because we would like to see whether it's more likely for thin rods to cluster or for disc-shaped objects to cluster. So we choose a whole bunch of these particles which extend from flat disks to thin rods. The equations of motion, and here I really don't want to dwell on this, but so there will be a certain element of rotational dynamics because you have this orientation vector. So the particles, as they move, will rotate, and their rotation is essentially governed by the local fluid field and what the gradients of the fluid field are. And there's going to be a translational motion, which in its simplest avatar is written in the following form. Here, keep in mind, Sujit, this is an answer to your question. Here, keep in mind that for the spherical case, this tau p is a constant, whereas for the non-spherical case, because as it moves, its orientation changes with the flow direction, this response time is a function of time. So on average, people have shown that this is right, but what we have to do is basically calculate both this resistance tensor and this rotation matrix, which is basically Euler angles what you did in classical mechanics as you move from the fixed flow frame to the frame of the particle. And yes, yeah, Pranay.
Particles don't influence the fluid.
No, so it's passive. It's passive. So, yeah. So, all right. These equations of motion. The only thing I want to stress are, are well grounded in the sense without this issue of self-propulsion, without the issue of Vicsek interactions, experiment, simulations, and theory sort of shows that these are the right sort of equations to work with for particles of this size, all right? So apart from that, I should rush a little, but apart from that, I impose a certain self-propelled velocity with a magnitude V0. So the particles along their orientation direction have a certain self-propelled component. So what the particle is trying to do in the absence of the flow, it would just go along its orientation vector with a velocity amplitude V0, but the flow is scrambling things up, all right? And like in the Vicsek picture, at every discrete time interval, delta t, the particles look up, see a neighboring distance r, and then try to figure out what the average direction is, and then they try to orient, all right? Okay, so that's that's roughly the model that one works with, and the turbulence of Navier-Stokes. Okay, I'll skip this, but this is, at the end if people are really interested. So all this is doing is comparing various simulation and theoretical results with experiments on these small particles which are not active to sort of show that up to modular adding activity, we are sort of doing all right with the equations. Okay, so good. So now in the last sort of few minutes, let's have a visual illustration of what's going on. So on the y-axis, I increase my radius of interaction. And along this direction, I increase, let's say, my Stokes sum. I'm just showing two Stokes, two sizes of particles just for easiness. Okay, so if you do not have a self-propelled velocity, and this was, why we needed all of those objects together, I'm not sure how clear this is, but then if you do not have any self-propelled component of the velocity, you hardly see, and I'll calculate the order parameters in a bit, but visually you hardly see the emergence of collective macroscopic flux. Okay? Now if I turn on a little amount of self-propulsion along its orientation vector, which by the way is also dynamically changing, if you remember the p hat, it follows what's known as the Jeffrey equation. Then for example, if you look at this guy, you see, and in case you were watching it at the start of the movie where they were all over the place, as time evolves, this sort of, shows rather interesting, certainly it sort of smells of collective motion, all right? Certainly it sort of smells of good football teams during this World Cup having a wave of attack. So it's really coordinated and they seem to follow what the other guys are doing. Okay, how does one quantify this? I'll skip this just in the interest of time. So the sort of simplest way to quantify this is to calculate what would be called the global order parameter. So essentially, we had about 1 million microorganisms in our flow. I mean, I'm calling them microorganisms with the caveats that I've sort of labored on. We seeded 1 million such chaps in our flow, and then we calculated the global order parameter, which sort of tells you how aligned they are. So here we have a plot, so I'm increasing the radius. So each of these plot is in the Stokes, the size of the particle and the shape of the particle plane. So at the bottom, this is really rod-like, this is really disc-like, and this is really rod-like. And here you start on the x-axis, you start from things which are really tiny to things which are slightly larger. And globally, each of these snapshots are done for different radii of interaction, all right? And here I'm increasing the self-propelled part of the velocity. So what you see is that you can begin in some corner of this sort of diagram where, so blue is basically 0, so there is no correlated motion. However, if you increase your radius of interaction to a certain optimal value, then you see these green patches which are value 1. So for example, if you look here, you already see that for certain shapes of the particle, and these boundaries are sort of slightly non-trivial, and we do not know where they come from actually, you see that for certain shape and sizes of these particles, there is an emergence in the Vicsek sense of completely correlated and collective motion. All right? So this is sort of ongoing work with Amal Roy, who's now doing his PhD in ISC, and Anupam, who's a postdoc, and Arnab Shah at Pune. But we sort of had a feeling that this would work. That's because a couple of years ago, we had looked at this exact same problem in 2D flows, but with only spherical particles, where we were able to calculate both the local and global order parameters. And we had found that you indeed saw, and that's the sort of color bar, so 1 means complete ordering in the Stokes and so here the plot is Stokes and the radii of interaction. So you see complete ordering very quickly. In 2D, the easy part is that you can do a lot of, you can sort of follow the parameter space much more closely. So this part, and then I'll just speak about chains in a bit. So what is the point that I'm trying to make? The point that I'm trying to make is rather strange that we now know a lot about passive particles in turbulence, all right? And so we are taking the sort of next logical step in some sense in trying to introduce activity in the particles. And when you do that, a naive guess would be, because the flow is so nonlinear and rapidly changing, that flocks may not be able to stabilize. What we showed was that this is not quite true, and that the turbulence can stabilize flocks. And more interestingly, so this was a paper which came out later, which were a bunch of experiments that people did in Sweden, if I remember well. And there, in a microswimmer suspension, they sort of, in their experiments, they seem to get a picture which is completely consistent with what Ashok and Divya and us we had proposed in the 2D case some years ago. What is missing, and I think this would be a crucial next step, is to understand what short-range hydrodynamic interactions between particles would do in this sort of model, and what happens when you have, more realistic models of particles which have internal degrees of freedom. So that's something that one would sort of like to look at going forward, and to see as you make your sort of microorganisms more realistic, the environment, thankfully, I can sort of go to town and say that the Navier-Stokes is a good description of the marine environment, but we probably would like to sort of develop the models of those particles which are surrogates of, for our individuals in the population, more realistic. So this sort of the fact that particles, I have 11 minutes, I should be done soon, but this is something that both Jason and I are very excited about. And so I'd still like to sort of discuss this briefly, if I may. So this brings me back to what happens when you have particles which have internal degrees of freedom, all right? And so the extended object that I'm going to just briefly talk about is a prototype for a chain or a fiber. At the end, I'll say, please don't take it too seriously. It's very far from a fiber, but for a title slide, it's all right, I suppose. Okay. So the preamble, if you remember, we saw this plot. What we saw was, what we know for a long time, and these two reviews I highly recommend, is the fact that Lagrangian techniques in the last 10, 15 years have told us a lot about turbulent flows, especially small scales in these turbulent flows. Now, these sort of measurements crucially rely on the fact that you make measurements with tracers, and as Amit sort of was trying to point out, these tracers sample the full phase space of the dynamics, all right? So if you wait long enough, and if you follow the trajectory of these tracers, you have information of the whole phase space of the flow. However, when you have inertial particles, that's one sort of particle that I had flashed this, you end up with preferential concentration, and you sample only a bit of that phase space. So you preferentially sample the flow. That is well studied. I mean, various groups have studied the role of inertia. It still continues to be a big industry for many groups to understand what inertia does in cloud microphysics. That's the model that we use. However, what happens to this preferential sampling when you have chaps which have other degrees of freedom? So, for example, if they're these sort of Trumbull-like models, or whether they are elongated objects which can run in tumble. So the simplest model that Jason and Dario Vincenzi sort of could come up with was a chain of point-like traces which are connected elastically with each other, right? So for usually for statistical physicists, harmonic chains are nice. Even in this institute, people like Abhishek and others have worked endlessly on trying to understand transport, heat transport, amorphous to crystalline transitions. All of these are well understood for harmonic chains in statistical physics. However, rather surprisingly, studies of what these chains do in fluids, in turbulence, has largely been untouched. Probably with good reason, Jason, but we don't know. Okay, so people in chemical engineering, of course, have looked at fibers, etc., but not this sort of baby model of harmonic chains. So here's my caveat: this is a toy model and far from fibers. Okay, so let's see what it does. I'll be done soon. So just to focus, so the chain is a repeat of this unit cell, let's say, and you just have elastic interaction between these two point-like traces. Remember, if there were no interactions, these traces would cover all of phase space. You'd have a completely homogeneous distribution of particles. Let's try and understand what elasticity brings to this story. So I won't go through the equations except to say that the equations of motion of the chain contain the information about its elasticity, and you can construct a Weisenberg number, which is the ratio of the elasticity timescale and the intrinsic flow timescale. Now, here Jason, not me really, sort of plotted the center of mass of chains of two different degrees of elasticity. Again, stressing these are chains made of traces. And you see, amazingly, that when you have low elasticity, the center of masses are uniformly distributed, as we would expect for traces. The minute you have finite elasticity, they tend to preferentially concentrate. And where do they concentrate? Not where heavy inertial particles would, but just the opposite. They tend to concentrate in vortical regions. How does that happen? Okay, so here sort of Jason looks at these are, here we were looking at the center of mass positions. Here, Jason plots the full chain length. As you can see, these are vortical regions. Away from the vortical regions, the chains are stretching out. And this will play a crucial role, as I hope to explain in the next couple of minutes. But if you were to look at these simulations, it's quite interesting. So you start with chains. The lower panel has a higher elasticity, and so everything stretches out as much as they can. The upper panel has a more intermediate elasticity. So there is, but again, for people who know, this is not a coil stretch transition that I'm trying to claim or show. But what you do see is that ends of the chains are pinned on these vortices. Here they coil up, but the free, both ends are free, but one of the free ends then slips out and starts stretching. All right, and when the elasticity is large, it's really, looking like a broomstick. So what would be a quantitative measure? So what do we have? We have traces which normally would sample uniformly the flow. Now we make these traces into little chains. It's like a bead spring model. And then the claim is, or from our, for various reasons, we felt that once you have an elastic interaction, they would tend to not preferentially sample anymore. They would tend to coil up like snakes do. And so one way to measure whether they are preferentially concentrating is through the Okubo-Weiss parameter, which if one were to calculate the fluid velocity gradient tensor of the flow, then this basically is the discriminant of the characteristic equation. So it has a certain formula. The only thing one needs to know is that if at any point in the flow you were to measure lambda, which is trivial to do, then the sign of that lambda would tell you whether you are in a vertical region or in a straining region. All right? A vertical region, lambda would have positive value. In a straining region, the value of lambda would be negative. All right? So what we did was, for various Weisenberg numbers, we measured the PDF of the lambda sampled by these chains for different sort of Weisenberg numbers. What we found was, so this is positive lambda, that there was indeed, and this is as you increase elasticity, that indeed chains tended to favor being in vertical regions than being in straining zones. Tracers showing preferential sampling. This is something rather bizarre. We also looked at stretching and the joint PDFs, which tell you a different story, but I'll probably skip that in the interest of time. This is sort of the basic message that I wanted to get across, is that if you take a chain which has no inertia, it might still end up sampling the flow preferentially just because of elastic interactions. All right? So, of course, this is really my last slide. Of course, the question remains, is this behavior universal? And this question can be asked in a different way. You have a given flow, and so it has a given time scale, it has a given length scale, everything is given. And you are allowed from a toolbox to construct your own chains. All right? So you have a given material, let's say material X, which has a given elasticity. Now you can take a chain of length Lm and put in 10 beads, so you will have small links connecting these beads, or you can put in 100 beads, and then the links will be even smaller. So the question is the relative length scale between your interbead link and the characteristic length scale of the flow, which, for example, in 2D would be the vortex length scale, does that play a role in this game? So what we did was, we measured the mean value of lambda, which you remember was this Okubo-Weiss parameter. We measured the mean value of lambda for different Weisenberg numbers, but parameterized by this guy. Lm is my fixed length chain. NL is the number of links in the chain. So for example, if there are 10 beads, then the number of links will be 9. So let's say Lm is 1 meter. So you put 10 beads, so you have 9 links. You can work out what the length of each link is. Now you can change the number of beads. You can put in 100 beads, and then you'll have 99 links. So your each link, or the deformability of the chain, will become smaller. So one way to express this is through this non-dimensional number. Our suspicion was that if the individual link size becomes larger than the vertical size of the flow, all right, then this preferential sampling would disappear. That's because there wouldn't be successive beads or a full link confined to a vortex, and hence they wouldn't curl up. So you might be trapped or pinned in a vortex, but because the next bead is certainly going to live outside the vortex, you will just do this and preferentially sample the flow. So this is sort of a numerical confirmation of the fact. So when the chain lengths are, the links are really small, that's these red curves, then you see that it preferentially samples, and as you increase the Weisenberg number, it's all the way up to 30, it increases and then saturates. However, if your interbead link is small or comparable to the vortex scale, then although it increases up to a certain Weisenberg number, after that, as the elasticity continues increasing, this phenomena takes over, where your chains are fully stretched and no two beads can be in the same vortex. And hence, again, this value goes down and becomes 0. It's a sign of the fact that you're again uniformly sampling the full flow. All right? Yeah. No, sir. So these are just tracers. Yeah. So it's in the equations you will see. Yeah. Okay. So this sort of brings me to the end. So it's a sort of the bare minimum that we were able to put. Okay. So this sort of brings to the conclusion is the fact that and this is the sort of party line that we are adopting for the moment, is that preferential sampling of flow via elastic interaction is something new, something which was not seen in the past, because all people thought in turbulence the only way you can preferentially sample a flow was through inertia. And secondly, all the important things that we are neglecting, with good or bad reason, is the role of inertia, because that would lead to a competing effect, right? Inertia would like you to do something, the elasticity would like you to do something. There's not even stiffness and those sort of things in flow. And more critically, we are neglecting hydrodynamic interactions between these beads. Again, that's open to criticism ranging from kind to really unkind, but for the moment, this is our first step. Okay, I'll stop here. Thank you.
So, thank you, Samriddhi. Although you were the last man to bat, you have been hitting sixes. Very nice talk. Questions?
Yeah, Neelima.
You already mentioned this.
Yeah.
I understand this too. Is the particle density and the fluid density equal?
No, these are heavy. I mean, this is tracer, so here it really doesn't matter. In the chain case or the flocking? Previous case? Oh, no, heavy particles, so the particles are more dense than the fluid. So they're not neutrally buoyant. So sorry, just to add to that, that's actually an interesting point, because when we are looking up at these sort of encyclopedia of animals found in the ocean, a lot of them are the opposite. They are floaters. But there's a whole class of organisms which are actually denser than the fluid. And so this sort of applies to those guys in some sense.
All that makes a difference to your preferential.
Exactly, precisely. So yeah. So this is in the class of heavy particles. I mean, okay, that's sort of, they still preferentially concentrate light ones, but the flow topology, the sample is different, so I'll put it that way. I mean, there is vertical trapping for light particles, for bubbles. Bubbles do get trapped as well, the light ones.
Any other questions? Yeah.
Okay,
I think everyone is exhausted. So let's take this chance to thank Samriddhi one more time.